In this video, we're going to look at three reactive intermediates of the methyl group called the methyl cation, the methyl anion, and the methyl radical. So methyl cation is where you have a CH3 and the carbon has a positive charge. This is called a methyl cation, or sometimes it's referred to as a methyl carbocation. Now, when there are two electrons on carbon, so two free unpaired electrons, paired electrons, then the carbon has a negative charge on it, and this is an anion, so it's called a methyl anion, or sometimes referred to as a methyl carb anion. And the last one is a radical. So radical has one unpaired electron. That unpaired electron is going to be on the carbon itself, and so this is called a methyl radical. Understand, like I said at the very beginning, all of these species are reactive intermediates. So we typically don't isolate them. They're too unstable to be isolated. They certainly, all three of them have been isolated, but for very short periods of time. And so we often will think about these as intermediates in a reaction progress, right, or a process. How do we form these? Well, if we take a look at methane, so CH3H, I'm highlighting one of the carbon-hydrogen bonds. And I need to remove that hydrogen. How can I remove the hydrogen? Well, I can remove it in one of three possible ways. Either the two electrons in that bond can move to the hydrogen itself. The result here is that carbon now has a positive charge, it becomes a cation, and then I also form a hydride, H-. Now, a second option is to move the electrons toward the carbon now. In this case, I get the carb anion, right? Carbon, or the methyl anion, plus a proton in this case, because now hydrogen has no electrons associated with it. And of course, my last situation is when I move one electron to carbon and one electron to hydrogen, right? So notice I'm using my fishhook arrows in this case. In the two cases above, I used the double barbed arrow to denote the movement of two electrons, and in this case I'm using my fishhook arrow to denote the movement of one electron. And the result is I get a methyl radical, and I also get a hydrogen atom, right? Neutral, right? Notice the first two give me charged species, the last one gives me neutral species. So the first two involve heterolytic cleavage. It's called a heterolytic cleavage because both of the electrons are going to one atom, and the other atom gets none of them. Whereas the bottom one is a homolytic cleavage. And of course, we know that generally speaking, a homolytic cleavage is lower in energy, right? Because it's producing species that are neutral toward one another. Now let's look at the structure of these reactive intermediates. We'll start with the carbocation, so CH3+. If we think about the geometry of that carbon, we know that it's attached to three hydrogens. So remember in our discussion about hybridization, when an atom has three things attached to it, this suggests sp2 hybridization. What's the geometry of an sp2 hybridized atom? It is trigonal planar, and therefore the methyl cation, the carbocation, is trigonal planar in geometry, and it looks like this, right? So I'm drawing the carbon hydrogen bonds perpendicular to the plane. So one's going to actually be in the plane of the board. Then I have another one coming out at me and another one going behind me. And then I have this empty p orbital, right, that exists. So a carbocation has an empty p orbital. It only has 6 electrons around it, so it's very unstable, and the bond angle is 120 degrees. This becomes important when we try to visualize the reactions that take place at a carbon center. Any of them that involve the formation of a carbocation, we know that the geometry is going to change to this sp2 geometry. So methane has an sp3 geometry. The methyl carbocation has an sp2 geometry. Now, if we think about the methyl anion, carb anion, we see that the carbon is attached to 3 hydrogens and a pair of electrons. So there are actually 4 pair of electrons around the carbon. This suggests sp3 hybridization, and the geometry of an sp3 hybridized atom is tetrahedral, right? So what does this look like? Well, carbon has a bond to the 3 hydrogens, one in the plane, one coming out at me, but all of them kind of pointing down a little bit, and then one going behind me, and then it has another sp3 orbital that has a pair of electrons in it. And the bond angle of a hydrogen-carbon-hydrogen bond is 107.5, so it's less than that of a normal tetrahedral, because the lone pair of electrons are taking up more space than the bonding electrons. And of course, lastly, we have the methyl radical. So in the methyl radical, one of the questions is, well, where does that lone electron actually reside? Does it reside in an sp3 orbital, or does it reside in a p orbital? And the answer to that is we're not quite sure. It could either be planar sp2 geometry, or it could be a rapidly inverting shallow pyramid in which the electron is going from an sp3 orbital and then gets inverted into another sp3 orbital. What it appears to be from measurements is that it appears to be trigonal planar. But we're not quite sure about that, and that's okay, right? I mean, not everything is known about chemistry. If it was, it'd be pretty boring subject to learn, right? So for simplicity, we're going to assume that it's sp2 planar, right? Trigonal planar in geometry, and therefore it has a very similar structure to that of the methyl cation, where you have a hydrogen that's in the plane, a hydrogen that's coming out, and a hydrogen that's going back. The bond angles are 120 degrees, and then you have this p orbital, but in this case, with the radical, you have an electron that resides in that p orbital. And so now we are getting used to thinking about the geometry of not just compounds like a methane, but also reactive intermediates like the carbocation, the carbanion, and the radical.